Okay, hello. Today let us start the third exit exam or gate exam questions for chemical engineering. This is a model questions for chemical engineering thermodynamics that's just prepared by Leta. So let's start. The first question says a refrigeration cycle is a reverse heat engine. So depending on this statement, which of the following has the maximum value of the coefficient of performance or COP for a given refrigeration effect? A says vapor compression cycle using expansion valve. B, air refrigeration cycle. C, vapor compression cycle using expansion engine. D, Carnot refrigeration cycle. Before explaining this question, let us initially see what is the heat pump cycles or refrigeration cycles in thermodynamics. So as an explanation, thermodynamic heat pump cycles or refrigeration cycles are the conceptual and the mathematical models for heat pump or utilized for heat pump, air conditioning and refrigeration systems. So a heat pump is a mechanical system that allows for the transmission of heat from a source at a lower temperature to a heat sink at a higher temperature. So we're supplying a higher heat to the system. So this law, a refrigeration cycle, goes beyond or does not obey the laws of second law of thermodynamics, because the heat is just flows from, according to the second law of thermodynamics, the heat is just transferred from high temperature to lower temperature, but the system says it is just from the lower temperature to the higher temperature system. So let's see the thermodynamic cycles. The operating principle of an ideal heat engine was described mathematically by using the Carnot cycle. So Carnot cycle is an ideal cycles which explains the thermodynamic systems, especially under the second law of thermodynamics. Actually, in Carnot cycle, there is an isothermal Carnot cycle and an adiabatic Carnot cycle. So for compression system as well as for expansion system. An ideal refrigerator or a heat pump can be thought of as an ideal heat engine that is operating in a reverse Carnot cycle, a reverse system, which means that there is a two-way system. A heat pump cycles and the refrigeration cycles can be classified as, both cycles can be classified as one vapor compression cycle using expansion valve, air refrigeration cycle, vapor compression cycle using expansion engine, as well as Carnot refrigeration cycle. These are the classifications of or the divisions of heat pump cycles as well as the refrigeration cycles. So let us see one by one. The first one is vapor compression cycle using expansion valve. The vapor compression refrigeration cycle involves four components. First one is compressor, second condenser, third expansion valve or throttle valve, and evaporator. Actually, it is a compression process, which means that this process is done by using a compressor whose aim is to increase or to raise the pressure of the refrigerant as it flows from an evaporator. So pressure is actually it is increased in an evaporator. Then there is a rising of refrigerant pressure. The high pressure refrigerant flows through a condenser, or actually the condenser acts as a heat exchanger before attaining the initial low pressure or going back to the evaporator system. Second one is air refrigeration cycle. So as a refrigerant, the working fluid is air, which undergoes no phase change in the units. The unit is refrigeration unit. So the main advantage of the refrigeration cycle is we can use air at any available cost, which means that the cost of air is just no cost. Actually, it's no cost, which means that low. Majority of the commonly used refrigerants possesses certain undesirable properties like corrosiveness, explosiveness, toxicity, and flammability. These are actually during operation, the refrigerant poses such undesirable properties on the surfaces of or in the refrigeration system. The disadvantage of the air cycles are there. Actually, the disadvantage of air refrigeration cycle is compared with other refrigeration cycle. It is low efficiency, or what we call it. It has a minimum coefficient of performance or COP. It requires large heat transfer and large quantity of air is to be circulated. Due to this all makes the air refrigeration cycles is beneficial, but it is disadvantageous or low efficient. Low efficient. The third one is Carnot refrigeration cycle. So the Carnot cycle is just, as I told you, Carnot cycle it's a reversible cycle which consists of two reversible isothermal processes and two isentropic processes. Reversible process, isothermal process, and the isentropic process. Isothermal process actually at constant temperature, and isentropic actually it is what at constant entropy. So depending on this Carnot refrigeration cycle compared with other types of refrigeration cycle, it has the maximum efficiency for a given temperature limit or within a given temperature boundary. Since it is a reversible cycle, all four processes can be reversed. All four processes means isothermal system for both compression as well as what we call it expansion. The second one is isentropic for both compression as well as expansion. Generally, the actual refrigeration cycles are less efficient than the ideal Carnot cycle due to the existence of irreversible effects. Irreversible effects such as friction, imperfect heat insulation, no heat insulation, and as well as because of the finite temperature difference that is maintained for a reasonably good rate of heat transfer in the refrigerator and the condenser. Due to this, the other actual refrigeration cycles like vapor compression, vapor absorption, as well as air refrigeration cycles are less efficient as compared with Carnot refrigeration cycle. From the four refrigeration cycles or heat pump cycles, the air refrigeration cycles are less efficient. So depending on the above mentioned statements or explanations, Carnot refrigeration cycles have maximum coefficient of performance as compared with other heat pump and refrigeration cycles. So the answer for this question is D. Let us proceed into the second question. Among the following, which is not considered as intensive properties? A. Chemical potential, B. Surface tension, C. Heat capacity, D. Refractive index. Before proceeding into the answer or providing the answer for this question, let us see what is intensive property and extensive property. Extensive property is the property of the material which depends on the amount of matter or mass, on the other hand, intensive property is the property of the material which is not depend on the mass of the material or amount of the matter or mass is considered as intensive property. So as an explanation, let us see what are the intensive systems. What are the intensive systems? Intensive systems consists of different thermodynamic properties. For example, color, refractive index, charge density, specific gravity, specific heat capacity, specific volume, pressure, temperature, specific internal energy, chemical potential, surface tension, standard reduction potential, thermal conductivity, specific rotation, velocity, concentration, magnetic permeability, melting and boiling points, modality, specific conductance are considered as intensive property. Those property does not depend on the amount of substance or matter. Actually, those are just measured. They are considered as the measured properties. The second one is extensive property is a physical quantity whose value is proportional to the size of the system. It describes all the quantity of matter in the system. For instance, the mass of the sample is an extensive property or quantity which depends on the amount of substance or matter. Dividing one extensive property by another extensive property generally gives an intensive value. For example, or for instance, mass, which is extensive, divided by volume, which is extensive, it gives or it yields density. So density is considered as intensive property. The extensive properties of the system includes amount of the substance or mole, enthalpy, volume, entropy, Gibbs energy, mass, Helmholtz energy, internal energy, spring stiffness, and heat capacity are considered as extensive properties in thermodynamic system. Therefore, the answer for this question is C, heat capacity, which is not categorized under or classified under the intensive property of the thermodynamic system. Third, the third question, it says, the theoretical minimum work required to separate 1 mole of a liquid mixture at 1 atmosphere containing 50 mole percentage each of N-heptane and N-octane into pure compounds, each at 1 atmosphere is determined as. So this question says, actually, the pressure of the system is given as 1 atmosphere, and the concentration for both N-heptane and N-octane is considered as 50%. So what is the theoretical minimum for the mixture? A, this is minus 2 RT ln of 0.5, B minus RT ln of 0.5, C 0.5 RT, D 2 times RT. So let us give an explanation. Let us determine the theoretical minimum work that is needed to a liquid mixture, since the mixture contains N-heptane as well as N-octane. The minimum work which is needed, or the minimum capacity of the work that is needed, is determined using this equation. So initially let us determine before proceeding into the work, which means that the minimum theoretical work, let us find or calculate entropy of a mixture. A mixture means actually there is N-heptane 50%, N-octane 50%. So entropy of mixing or changiness of mixing is determined as is equal to minus R, the summation of the mole fraction xi times ln of xi. So xi for heptane is given as 0.5. Since we have two mixture, we can consider N-heptane and N-octane xi, which is equal to 0.5. for heptane, xi is equals to 0.5 for octane. So x heptane, which is equals to 0.5, x octane, which is equals to 0.5. So the change in entropy of the system, which is equals to minus r in bracket 0.5 ln of 0.5 plus 0.5 ln of 0.5, which gives us 0.5. Since ln 0.5 is common, 0.5 plus 0.5, it gives us 1, so which is equals to minus r ln of 0.5. So then work is equals to, simply work is the summation of temperature times change in entropy of the mixing. So T is, actually we can take T as a constant minus RT ln of 0.5. So work is equals to T times change in S, which gives us minus RT ln of 0.5. So depending on this equation, or depending on this explanation, the correct answer for this question is B, which is the minimum work required for a liquid mixture is minus RT is equal to minus RT ln of 0.5. So for this stage, let us proceed into the fourth question. The fourth question, it says, if the vapor pressure at two temperatures of a solid phase in equilibrium with its liquid phase are known, which means that the solid is just in equilibrium with a liquid. Actually, there is a mixture. So then the latent heat of fusion can be determined by the A. Maxwell's equation, B. Vallar equation, C. Nernst heat theorem, D. Clapeyron-Clausius equation. Actually, in thermodynamics, there are different types of equations. Especially in thermodynamics 1 as well as in thermodynamics 2. But those equations are, there is a Maxwell equation, which means that the four important Maxwell equation, Vallar equation, which means that this is the chemical engineering thermodynamics 2, both of them, Maxwell as well as Vallar, Nernst heat theorem, and the Clapeyron equation. So from this choice, which one is correct? Before proceeding into the answer for this question, let us see which one is correct. Let us discuss the relationship between the latent heat of fusion and the vapor pressure at two temperatures of a solid phase in equilibrium with its liquid phase. The mathematical equation that relates the aforementioned parameters can be explained as follows. Let us look at, as an explanation, the Clausius-Clapeyron equation shows the relationship between the saturation pressure, temperature, the enthalpy of evaporation, as well as the specific volume of the two phases are involved. A specific volume actually for the two phases means as either for the vapor and liquid as well as for the solid. Actually, if it is vapor, we can consider it as for the liquid as well as for the gases. This equation provides a basis for calculations of properties in two-phase region. It gives the slope of a curve separating the two phases in the pressure-temperature diagram. The Clausius-Clapeyron equation can be derived in different ways. So let us see how to derive or how to find the relationship between the latent heat of fusion with temperature as well as pressure. This is the pressure-temperature diagram. The stage where the solid as well as the liquid is just contacted or forms an equilibrium. So let us start an explanation. The method given below involves the use of Maxwell relations. So in order to derive the Clapeyron equation, or in order to get the Clapeyron equation, let us see the relationship, the Maxwell relation. In Maxwell relation, the partial of pressure with temperature at constant specific volume, which is equals to the partial of entropy with partial of a specific volume at constant temperature. Let us consider this system, which means that change in pressure with temperature at constant specific volume, which is equals to the change in entropy with specific volume at constant temperature. Let us consider the change of state from saturated liquid to saturated vapor of a pure substance which takes place at constant temperature. Let us consider the system at constant temperature. The system at constant temperature. If the temperature of the system is constant, dP, which means that the change in pressure by change in temperature is directly equal with the change in what we call it entropy with the change in specific volume. I mean that we are considering saturated liquid with saturated vapor. So Sg minus Sf, which means that entropy of the gas minus entropy of the fluid. Yeah, the fluid, which means that for liquid, or you can use liquid, vapor, specific volume of the gas minus specific volume of the fluid. During the evaporation, the pressure and the temperature are independent of volume, so we can consider this theorem. So where Sg is specific entropy of saturated vapor, Sf is specific entropy of saturated liquid, Vg is specific volume of saturated vapor, Vf is specific volume of saturated liquid. So depending on initial equation, the change in entropy of the system, which means entropy of the gas minus entropy of the fluid or the liquid, which is equals to Sfg, because this is actually one way to write the entropy of fluid, liquid, gas is equals to the evaporation, which means that HFG divided by T, and Vg minus Vf, specific volume, the change in specific volume, Vfg, where Sfg is increase in specific entropy, Vfg is increase in specific volume, and HFG is latent heat added during evaporation at saturation temperature. So equation 1, this equation so initial equation 1 is valid for the change from a solid to liquid or from solid to vapor at very low pressures. If we assume the specific volume of the gas is directly equal with or approximately equal with specific volume of fluid gas, and the equation of the vapor is taken as PV is equals to RT, then equation 1 becomes, we can write it like this equation. This equation, we can write it as like this one. The change in pressure divided by change in temperature, which is equals to the latent heat of gas with saturated liquid divided by temperature times volume of the specific volume of the gas, which is equal to HFG times pressure divided by RT square. In place of V, you can take Vg is equals to VRT. So let us see how to just manipulate this equation. So R, not actually Vg, which is equals to VFG. So from this equation we can understand that PV, which is equals to RT. So in place of PV, which is equals to for the gas, which is equals to what we call it RT. So in place of Vg, you can find Vg is equals to RT over P. So you can calculate it by using this equation. So from this equation, the latent heat of vaporization, what we call it for the solid liquid, which is equals to RT squared divided by P dP by dt. So equation 2 may be used to obtain from equation 2 may be used to obtain the enthalpy of vaporization. This equation can be rearranged as dP by P, which is equal to HFG by R times dt by T square. So integrating this equation, dP divided by P, integration from P1 to P2, which is equals to integration from HFG is constant divided by R, integration from T1 to T2 dt by T squared. So from this equation we can get it yields ln of P2, because integration of 1 over P dP, it gives us ln of P2 divided by P1, which is equals to HFG over R in bracket 1 over T1 minus 1 over T2. This equation is considered as Clapeyron equation. This equation is considered as Clapeyron equation. So from this equation we can understand that the equation that relates the latent heat of vaporization, or the saturated for solid with liquid, is related by using Clapeyron equation. So for this, thank you for your attention, and we will this is the end. Thank you.